Okay, so I'm recording, and what we're going to do is talk about, like I said in class, we're going to talk a little bit about protocols, what those are. We talked about the 7-layer model yesterday, and I'm going to spend more time on counting and number systems than this material does. So I want you to get, I want you to have more time for that. Okay. So what we have to think about here when we look at communications is, and all of our models are we say they're informed by this information. So the way we think is governed by the fact that a message has a source or a sender, and it has a destination or a receiver. Every message that we send, no matter whether it's spoken or written, presented, it has those properties. So what we have to do is we have to figure out how that message is going to be translated, how it's going to be controlled, and how it's going to get to where it's going to go. And so we have to make a lot of decisions beforehand. And when we think about communication, you know, back in the day when maybe Greek or Roman armies were coming over the, you know, they were in Europe or whatnot, and they had messaging systems that were actually tall platforms where a guy would climb up and they would build a fire on this tall platform, and he would use a series of smoke signals to make the to send a kind of a proto Morse code. But there would be specific things that he would code for. And the reality is that if I got up there on a tower and I just started sending my own smoke signals without any prearranged knowledge changing hands, I would not be able to effectively communicate, would I? I'd just be sitting up there flapping in the wind, right? I got to have some rules in order to establish and maintain communication. So both of us, both the sender and the receiver, have to know what's being done and what to expect before we can actually communicate properly. And that is the whole nature of a communication protocol. Whether it is the microcode that happens, the micropulses that happen when a link is brought up, right? There is a pattern associated with even bringing up one link between a computer and a switchboard. Those devices have to negotiate a connection with each other, and they have to know whether they're going to be transmitting at 10 megabits per second, 100 megabits, or a gigabit per second. So there's a pattern there that those devices have to follow in order to decide which transmission speed is going to be the prevailing speed. And it's basically a rule set that says when this line is energized, when we detect a signal, we have to wait a certain number of pulses before we begin to communicate using a series of known pulses. What is the maximum transmission speed in duplex that I can use? The other side reads that, and maybe it's not a gigabit port on the other side, it's a 100 megabit port. So it doesn't have the language necessary to talk gigabit, right? If it's not designed to work that way, it doesn't have that language. So effectively, it ignores what it doesn't understand. And that happens a lot of times in communications protocol, because we just have to know what to ignore. We only listen for certain things that make sense to us. So that happens in the line protocols. And they're even called line protocols, right? This is what we do on the line. We're not going to go into that. Wikipedia documents it very well. So you can read all the Wikipedia you want.
Now, as far as the third part there'll be a channel / media. Media is practically all of the electronic devices in the network, correct?
No. Media is specifically transmission media. So
Messenger, the program itself, or
messenger. No. No. So there's a sender, source, destination, receiver. These are the endpoints.
right?
Um,
So path of communication, that's got to be not only the host, but it's got to be the router and the switch involved, as well as the network cable and the cabling in the ground and the repeaters in between, correct?
So, well, we want to think about it I mean, yes, while that's true, I want to think about the communication network in a very, very simple form. Okay. So I haven't built anything else except basically 2 NIC cards and a cable at this point. That's my simple network.
Got it.
You got to keep it simple.
Okay.
If it was a wireless network, it would be 2 wireless cards that have antennas on them and that are connected to 2 computers. We keep it as simple as we can.
Got it.
Because what we see is that we have to build a layer 2 on top of that. And so we have to get this layer 2 to work before we get to layer 3. Layer 3 is where we get between those 2 points.
Okay.
Yeah, okay. So rules, this is important, right? This is where we began to go, okay, how do I communicate a certain message to somebody? What do they expect to hear in order to know what to do? That's where we start establishing what it is we're going to do, because remember, all of this stuff is automated. The whole process that we're building, that the engineers have come up with, the solution to get messages from one place to another, do not rely at all on human intervention. They're all automated. So everything has to be algorithmic. And an algorithm is steps that we take to solve a problem. So all of the communications have to be done completely in an automated way. And so because of that, we have to have a common language and grammar. We're absolutely intolerant of a communication that does not go by some standard. That's the purpose of all the standards making bodies out there, no matter what they do, whether it's ITU and it's talking about telecom standards for telephone networks, whether it's or telephony devices, whether it's IETF, Internet Engineering Task Force, IEEE. IEEE is the standards body that does all the electronics, electronic devices, and then as far as IP addressing, it has its own standards body. They all have a purpose.
Does ICANN literally handle everything for the entire world or just America?
Aaron handles America, the American Registry for Internet Numbers.
Mhm.
I can. Let me think here.
Because according to this, where did I see that? Based in the United States, ICANN coordinates IP address allocation, the management of domain names, and assignment of other information used in TCP IP protocols. Is that just for America, or is that for the entire world?
No, I don't think so. I have never had anything with ICANN or done anything with them. Let me look them up real quick. That's a good question. Let's look up ICANN real quick. Yeah, this is so ICANN is domain name is the okay. So ICANN is a domain name system component that is equivalent to IANA, which is the IP address component.
Mhm.
So yeah, they're going to control the global DNS system, but that DNS system is broken up into regions. So they're going to be a global standards making body, but it's still up to the regional providers to apply those standards in their own regions. Something that's interesting that if you look at DNS is that the DNS system is what happens is they actually go in and they will change the security keys for the DNS system. And this is it's called a key signing ceremony. And I mean, I'm going to tell you what, people come from all over, like all over the country, and they show up at either a site on the East Coast or the West Coast, and they alternate. They go from East Coast to West Coast. And I think they do it once a quarter. And all these people show up and they have a meeting and they go over the procedure for changing the keys. And then they go into a vault and everybody has to unlock their little locker with the key they have. And someone else uses their part of the key to unlock the other guy's locker. And then they have their keys that they get. And they have to read off everything. I mean, it is a whole orchestrated ordeal. It's pretty amazing how it goes on. And it
shows on a ship.
Huh?
It's like the nuclear codes on a ship.
Oh, I think I almost want to say that I think the DNS security key is more secure than the nuclear codes.
That's kind of scary.
I really think it is. I watched one of those one time, and it was like a 4-hour process that it takes to get the security keys updated for the new quarter. I mean,
Wow.
it is. You can get the script, and you can see exactly what's done in what order, who does it, and they run this whole thing. It's an orchestrated show.
And then when you think about it, if anybody managed to get access to that, could bring the entire world to a screeching halt.
Exactly. I almost would wonder if it's more secure than the nuclear codes. Yeah, it's pretty cool. But so yeah, so that's going to be the people who basically they develop big systems, and then the regional authorities actually apply. I think that's right here. Registry operators. But anyway, this is a whole nother area. You know, if
Okay.
you're interested in that, you can become a member of these organizations and you can take a part in that. You know, in looking at the DNS stuff, they had a place where anybody who was interested could actually sign up and nominate themselves to be considered as part of the pool of people who get picked to do that stuff. So it's a community operated organization. So okay, here's another component.
Yeah, you were right there.
Yeah, okay. I want to go. I'm jumping around here, but I'm giving you some important things to know. Okay. This message delivery, unicast, multicast, and broadcast, those are extremely important terms. The unicast message is a message that I would send to another person. I know the destination of the person that I want to receive the message, right? That's a unicast message. It's a note from me to you. A multicast message is a note it's like a newspaper or a magazine. I write an article, and the only people that get the message are people who subscribe to it. Well, one way to think about multicast is another way is subpub, right? So I subscribe to a publication, subpub. That's a model. And an example of a multicast traffic on a network could be when I have a router and my router has information about all the different routes that it knows about and connections that it knows about apart from itself. And there's a change to that information. How does the router get notified of the change? And the way that that happens is multicast. So that's a piece of traffic that only the router gets. It doesn't send it to anybody else unless it's another router. It learns about change on the network. And all of my users that are there, they don't have to deal with that. They don't have to sort through that traffic. But we have special addresses that we use for multicast traffic. And then we have broadcast. This is the type of communication that we will deal with in this class more because it is traffic that's sent to everybody. Okay. This is the way that our switches communicate. They communicate in unicast mode and broadcast mode in most cases. So my switch is going to be designed to basically communicate. If it knows where the message goes, it sends a message. But if it doesn't know where, it will broadcast the message. All right, so it goes everywhere. And it's really the messages all really fall within those types. That's something to memorize. This is something you want. Multicast is an example of it, could be a router to router. But the definition of it would be, well, one message that goes out to some people, not all people. And so the way we know is that you can think of it as a subscriber to a publication, right?
A real world example is like what we do in Discord.
Yeah. Yeah, that's a perfect example of it.
Because Discord has obviously gobs of users out there, but you only subscribe to that one server so that, or channel, however you want to phrase it. So when he sends a message out, it only goes to us as the people that are subscribed to his server, not to everybody in the entire Discord universe.
Right. Another perfect example of that is what's known as the Fediverse. Oh my gosh, what's that program?
Facebook?
No, not Twitter, but Mastodon. Mastodon. That's
Mastodon?
yeah, Mastodon.
What the heck is that?
It's a federated social networking where I could actually be on any server and I could subscribe right to any other server, and I get notified when those servers have particular traffic. I'm in a federated universe. So it's the exact same model. So if I'm using Mastodon, in this particular case, there's no centralized. So even in Discord, there's a centralized server that basically where my server lives, right? Mastodon is fully decentralized. I could run a Mastodon server on my computer hardware. Somebody else could run one on theirs. And those servers may be able to talk to each other, or they may not be able to talk to each other, depending on what the users want to do.
So is it almost harkening back to things like eDonkey, or I'm going to use the phrase, this is file sharing systems?
Peer-to-peer?
Ish, yeah.
Yeah, it's very similar to that.
How are they communicating? Are they communicating in hashes, or what are they doing?
It's packets, but it's just when I subscribe to a server, I'm giving that server permission to basically send a request over to the other one and accept messages from it. So yeah, it's very similar to peer-to-peer.
Okay.
In that way. It's, these types of models that we make, they can be applied all over the place. And so part of understanding the way these things work is you got to look into how stuff works, like peer-to-peer file sharing or Mastodon or Twitter, and like draw the conclusion that, oh yeah, this is a very similar way that this works. It helps you understand, right? All this these different ideas. Okay, and then we'll look here at these things. These are functions that the protocol does. Okay, so my protocol that I use, and a way to think about protocols is just use the word rules. All right, whenever I see protocol, I can substitute the word rules. Okay? I talk about all kinds of different protocols. What I'm really talking about is a rule set. All right? And so when I have a rule set for a network protocol, I'm going to be able to basically do all these things with it. So that is the TCP protocol suite. Okay. It's called a protocol suite.
When they designed this, why did they get so granular, considering that flow control, sequencing, and error detection practically all fall under the same category of reliability? Because if you want to be guaranteed delivery, then obviously all of those other conditions underneath reliability have to be maintained.
Well, yeah. And the reason why they got granular there is because in order for that, it's exactly what you say. In order for me to do that, I have to do all those things.
Okay.
So that was the minimum package that I could put together and establish all those things.
Okay.
Right? It was the minimum. I had to have the minimum. So this idea of sequencing, right? I have to understand that at some point the packets could get out of order. So I have to establish some protocol or some set of rules to put those things back in order. TCP does that. UDP does not do that, right? So I build that idea in there that I have the ability to do something different if I want to. Okay. So here's the hierarchy of that. Ethernet is a protocol, but it's also a standard, right? So I could have the most common thing we do is when we talk about Ethernet, is we talk about an Ethernet cable. And a lot of times the Ethernet cable equates in our mind to that little rectangular plug that's an RJ45, right? This RJ45 plug, and we say, well, this is Ethernet right here. Well, not really. Ethernet is the standard by which I send the data. I just happen to use a cable and an RJ45 and a category 5 cable and an RJ45 plug and an RJ45 port that's powered to a certain set of voltages, right? That's my quote Ethernet standard. Okay, I could send Ethernet over wireless. I could send it over copper. I could send it over category 5, 6, 7, 8.
Fiber.
I could send it over fiber. I could send it over Heliax if I want to.
What is the voice over IP?
Voice over IP?
Yeah, no, it's VoIP, isn't that what it's?
Yeah. Yeah, so that could be an example of a protocol. But it is specifically a protocol designed to handle voice traffic.
So Ethernet doesn't necessarily mean that physical cable that you look from.
Right. The physical cable is it's part of a standard, right? I mean, it's there. If I wanted to, the cable, I can be assured because of standards that cable is the same. If I get a category 5 cable or a category 6 cable, it's going to meet the minimum specifications of that standard. But we call it Ethernet cable like we call a photocopier a Xerox machine. Right?
That's very true.
Because here's the deal. Look at this.
Calling a soda a Coke.
Yeah.
Yeah. Or a car. Are they all the same? We got the same thing as the Volkswagen. Technically, they're about the same company, but I'm not gonna go there.
So if I'm at Amazon and I go and look for an Ethernet cable, I'm gonna get, I don't know, maybe I got some blue, some black, right?
4.7 million hits.
Now, if I go to show me cables, how do you want your cable? by category, by use. Right? So let's go by use. If I go just into networking,
Hey,
I can keep drilling down. Patch cable is different than bulk cable. Bulk cable comes on a spool or a roll. Right? If I
so
look
patch
at
cable is just terminated and bulk cable obviously isn't.
patch cable is shorter and terminated and usually flexible. That's the key on patch, is it's usually stranded wire inside.
Oh, whereas that's solid conductors, but it's eight
Mhm.
conductors versus multi-strand in patch.
Yeah, so
Okay.
you start looking at bulk cabling. Okay, look at this. Right, stranded is right here. Solid, stranded, shielded, outdoor, plenum, indoor. Plenum means that it can be installed in a plenum space, which is a crawl space. So there's several different kinds of plenum cable. One is that the plenum has a shielded member inside that could support the weight of all the cable above it, and it won't snap. So I can have a certain rated length of run.
Yeah, fire rated plenum, right?
Fire rated, yeah, all plenum has to be a minimum fire rated specification. I might want to have shielded cable, which adds more shielding around the inside. All of this cable meets the Cat 5 standard. Right? It's Ethernet. But we can get very, 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 very detailed in how we describe it and what it's made out of and what it's used for. This is another whole world that this opens up. It's just the manufacturing, delivery, and sales of cable itself. We used to buy this, I would get this shielded, solid core cable that is gel filled. And we'd buy 10 spools of it a quarter. I thought gel filled, yeah. A gel filled cable will prevent water from entering the cable should the jacket perforate.
Okay, that makes sense.
Yeah.
Good for outdoor runs.
Outdoor runs.
Yeah.
And then you can get direct burial cable,
Mhm.
which allows you to put it straight under the ground.
Instead of putting it in conduit.
Yeah. So how do you want your cable? It's kind of like, how do you want your steak, right? There's a lot less choices on the steak.
So. Right, so with Ethernet, you're talking about all of the components necessarily involved in network communication.
Mhm. Yeah.
Okay. Now, does that govern the routers and the switches and the modems, or is it just strictly the equipment that you would find on end user or post usage only?
So yeah, it does. The routers, okay, so switches simply switch. They don't really have a knowledge necessarily of the Ethernet standard, other than the fact that they're getting the data frame.
Okay.
Layer 3 devices like routers will be able to use the Ethernet standard to send packets, but they could also load up other modules. At that point, it's just software. From the halfway point of layer 2 all the way up to layer 7, it's software. So I could use other standards besides Ethernet.
Okay.
Ethernet's the most common, but there's also SONAT, ATM. There's other standards that govern how my network sends data.
Okay. So this is, the Ethernet is practically, if you were to really just flip this over on its head, the Ethernet is the foundation of the network as a whole.
Yeah, it's the most common way to transport data. But not the only way.
Right.
It's just the most common because it was so well designed that we could build all that reliability, all that addressing, and it's just stood the test of time.
Mhm.
Because it was so well designed, and I don't see that it's going to change anytime soon. It's just still going strong. Okay. So, another thing to look at, and I'm not going to go over all this, but I want you to be sure you look at this chart. And it's just where the protocol suites are. Let me go back. You're going to get a lot of acronyms. And we're going to be kind of all over this thing. But this chart right here will help you understand where the different components live at, what layer they live at. So we're going to get into this operation of ARP, or address resolution protocol. There's your Ethernet protocol right here. It's on that data link standard. But we have to build more protocols in order to make the different things work the way that we want them to work. So here's our IP, our internet protocols, which you're addressing. And delivery, messaging, and routing. So there's a lot more that goes on this chart. The more complex that we want to get in terms of understanding the network. But these are the ones that we're going to be focusing on, and the ones that make what we do functional. Yeah. There's not really a whole lot in the transport layer, but these two, TCP and UDP.
Can I ask a question, please?
Sure.
The internet layer, I see the routing protocols. I have seen job descriptions that want you to know some of those OSPF and BGP. So is there a reason why they want you to know those particular routing protocols?
Because they're the most common. The OSPF protocol, open shortest path first, that is the prevailing routing protocol in the world right now. It doesn't mean that it's the best. Like there's certain situations where I may not want to use it, but it is the most common. That wasn't always the case. What happened before that was the IGRP, and that was the most common before OSPF was invented in the 2000s. The IGRP was in the early 2000s, and before that, RIP networks were not as complex. So we could use a very, very simple protocol. And so that's not even on this chart anymore. But we can turn RIP on a router, and it's router information protocol. And it's a very, very simple protocol that we use for routing.
What is BGP then?
BGP is Border Gateway Protocol. The Border Gateway Protocol is the protocol that we use to connect networks together. So I'm going to run BGP at my telephone company or my internet service provider. to get the communication onto the global network.
And so BGP is kind of, I'm gonna frame it as regional base.
Yeah. I would, so if I had a small internet provider, and I had, and I wanted to communicate with, let's say, AT&T, who's a bigger provider, I would run BGP. And what would happen is this, in the terms of a routing protocol, it's a very simple protocol. It comes up and it advertises a certain route to the next guy. And that guy may be a bigger provider who his whole goal is to basically be a router for the whole internet. And so he's just going to be sitting there peering with all these other network providers through switches. And they'll all run in the same protocol, which is BGP. And it's all about creating a peer relationship. So that's that peer-to-peer networking again that comes up. That's BGP.
Level of CCNA do we learn about the routing protocols? But there is a level, right, that we cover
Yeah.
that, but not in this course, correct?
We'll learn about routing protocols in we'll learn about them in this course. We'll learn more about them in Cisco 2. And then we'll learn about BGP and WAN in the Cisco 3. Mhm. And then once you get into the engineering side, which is a CCNP, if you continue on and study that, you're going to get more into, you're always going to be alternating between learning more about the switches that make things work and then the routers that allow them to communicate. It's always going to be this ratcheting between the two. Because when you get all into it, the switches are what controls that's what do all the work, not the routers. But yeah, you'll get routing protocols they're designed and used based on how we need to communicate. The idea behind OSPF is that I have a protocol that is more automatic. It allows failover to be an automatic thing. And so it just gives me more features. And so I implement it.
And IGRP is just, it's put in here just as a reference point of this is what used to be.
Yeah,
It's not used anymore.
it's still used. It's just not used as much. EIGRP is a distance vector protocol, and it's basically designed to, I might see it on networks that are middle provider networks, where I don't have as many choices, for instance, for my routes to go. And I can control it with just understanding the distance between the connections. So I control it with a single metric. And that's, EIGRP is going to be a little more hands-on. OSPF is link state.
Okay.
If the link is up, we're going to calculate the shortest path for it to travel, for the data to travel, and we're going to send it that way. So it's a more of an automated protocol. And then you have all this stuff at the top. And it's all application layer. So even if the application doesn't do that much, right? Think about DNS. At the heart of DNS is simply a lookup. I'm exchanging a query string for an IP address. And that happens, but the issue is that happens every single time that my computer wants to send a message to a destination that it doesn't know where the destination is. I have to use something to make that happen, and I use DNS.
Considering you can put in an IP address or you can put in a text string
Mhm.
for a query. Those have all moved past the capability of being put in a binary string and find it, or can you put in binary and it will still find it using binary?
Well, technically what you're doing is when I go in here and I put in a numeric IP address, like 10.19.6.254,
Right.
right? That, my network layer is taking care of the binary conversion for me.
Okay.
So it's ultimately getting to binary. I just don't have to do it.
Were networks ever? I mean, obviously this is an engineering thing, but were they ever communicating binary outside of in the routing portion of it, as far as, obviously you have to addressing and translating into binary in the packet sense?
Well, it's all binary. It is all that way. Everything is binary.
Mhm.
The fact that we convert it out into something else is another layer, but it is binary even now.
Okay.
Because that electronic medium can only transmit one thing,
Right.
electricity. All right.
Okay.
So you're leading me right into my next area of discussion, Brendan. And I'll skip the standard stuff. Okay. Oh, I want to say one thing about models. We talked about the 7-layer model yesterday. There's also a 4-layer model called the TCP/IP model. So here's the difference between the two. They're very similar. This is a way of thinking. This is also called the DoD model. Okay? The DoD model, mainly this is from an analysis standpoint. If I'm going to analyze what's going on in my network, and if I'm a remote analyzer, if I'm looking at what's happening on the network, I don't really have a whole lot of control over the physical side of it. So I just don't even really think about that. If I'm seeing network activity from afar, obviously the network is powered on and cabled, or the traffic wouldn't exist, right? So here's my model. If I'm the engineer and I'm designing the network and I'm designing the communications channel from the physical all the way up, these are the things that I look at and the steps that I break things into. But if I'm the analyst and I'm just trying to understand what's going on the network and how it's interacting, this is the model I use. It's much less complicated. Basically, I'm saying I'm taking that all the stuff that happens at the application layer and I'm grouping it into one area. This particular model is not necessarily taught too much because we want you to learn all the different layers. But in terms of when you graduate and you get to the area where you're an analyst, your mind is probably going to spend more time using this model. It's 4 steps. So I wanted you to see that it's always there, but a lot of times it's not clear. as to why we have two different ways of thinking about networks. I'm usually focused on, as an analyst, the meat and bones of what I do might be in this area right here. Is what's going through the network. What is maybe if I'm securing the network, I'm going to be really focused on this right here. I'm not going to care as much about the specifics that's happening in this box. Not always. Just another way of looking at it. Okay. When we get down here, I have to get my data on and off the wire. And so I have to be able to identify components at a very granular level. And we use what's called a MAC address in order to identify a component. And so this is where we get into our numerical systems. So I have a device that I need to identify. And in order to do that, I have to give it a number. Okay, and so what the engineer decided on was that I would set aside some storage space, and I would be able to store a unique number here. And this is 6 bytes. Okay, and I put X's there. And traditionally, the MAC address is distinguished by 2 digits separated by colons. And so each one of these positions of 2 digits represents 1 byte of information.
And the byte is 8 bits.
The byte is 8 bits. That's right. So the MAC address is 6 bytes. 1 byte is 8 bits. The 8 bits are represented by pulses. Hello. Wait.
We're supposed to be here at 10. I'm not
Okay.
early.
Oh, okay. Yeah, just have seats and we're just finishing up. Okay. So about 6 bytes, and this is just so okay. One thing to know is that this 6 byte value is arbitrary, right? Some engineer, somewhere in the world said, okay, if we're going to start numbering off network devices, and we're gonna make it a globally unique number, we got to make a big enough number so that that's true. And so they said, well, how big should it be? Right. So they talked about that for a little bit. And somebody put forth, well, 6 bytes should be enough. And what they say, oh, that's way too big. Right? Because that's what they always say when they throw out a number out. You'll never fill up what? Put whatever you want there, right? You'll never fill up that 10 megabyte hard drive, right? You'll never have enough files to fill up the 40 megabyte hard drive. And then why did I trade my 32 gigabyte iPhone, which worked perfectly, to get a 128 gigabyte model? Okay. Or do I have more than that? I don't even know. So they said, okay, 6 bytes should be enough. Matter of fact, here's what we'll do. Well, let's figure out how many bytes we can have in each number, okay?
So the total of that MAC address.
Uh-huh.
1, 2, 3, 4, 5. So there's 6 pairings. And the total of those 6 pairings, those 12 unique characters, is a total of 6 bytes. It's not 6 bytes per pairing.
Right, it's 6 bytes total. So each one of these is a byte.
Okay.
Each character represents half of a byte.
All right. Okay.
Okay, so I'm gonna go ahead and say half of a byte is a nibble,
Right.
because obviously that's what a mouse would eat, right? He can't take a whole bite, he just takes a nibble, right?
Okay.
Okay. So that's our half byte. Now, in reality, what I can do is I represent that by a hexadecimal number, okay? And here's why I do it. When I start counting in binary, okay, I'll start with 0 and then my next value is 1. Okay. And what I like to do is I'll just go ahead and I'll use 4 right there. That is my representation of 1 nibble. Or these 4 placeholders. What I'm doing is I'm going to count. And I'm going to get that 1 digit right there, that X. Now, when I count, and this is where your numbering notebook comes in, okay? You want to use it to practice counting. And if you think, oh, I know how to count. Okay, well, the first class I took at Texas A&M University was a class to teach me how to write my ABCs and 1, 2, 3s in 2 different script fonts. It was called Engineering Graphics. And I got to learn to write my letters all over again. So I stand behind that authority by asking you to learn how to count, okay?
So the
Yeah.
total that any maximum amount that could actually be as a nibble is 1, 3, 7, 15.
Yeah,
I guess technically it would be 16 if you wanted to move to the next place.
so how many items can I hold? 16. What's the range? 0 to 15,
Right.
okay? So yeah,
0 through F.
0 through F, right. So here's what I'm gonna do. I'm gonna take my binary and I'm gonna, what I get to do here is I can only hold in 1 bit, I can only hold 2 states, 0 or 1, okay? All right. So as I count, I've got a 0 in the first spot, a 1 in the second. I want to add a bit. I have to use my second place to put the value there, and my first one turns to 0. And once you catch this pattern, you'll never forget it.
0, 1, 0, 0, 1, 0, 1.
Look at the
0, 1,
last.
1, 1.
Look at the last bit. It's going 0, 1, 0, 1. That pattern will continue all the way through 0, 1, 0, 1, 0, 1, 0, 1. The second to the last bit is always flagging 0, 0, 1, 1, 0, 0, 1, 1. We'll see that every time. So I want to add a bit. I have to use my third place to turn that bit on. And these 0 out. Because I can only hold 2 in each space every time I add another one, I gotta turn the next one over.
Oh. Okay,
Okay, this last bit is cycling 0, 1, 0, 1, 0, 1, 0.
Okay.
1, 1, 1,
then we start with 1, 0, 0, 0.
1, 0, 0, 0. 1, 0, 0, 1. We repeat the pattern again. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9,
A.
A, B, C, D, E, F. Here's what I want to do. The problem is I want to store as many values as I can in one little half byte. This is my half byte. Here's my value, 0 through F.
So these, when referring to these as bits, or are these in a MAC address or in general for our purposes in networking? Are those characters representations of values, or is it just characters?
It's representations of sequences of bits.
Okay.
So in real life, it is voltages on a wire
Mhm.
that hit a certain threshold that tells me that that's a 1. And then there's a voltage that's down here in the doldrums that doesn't hit a threshold. It's a 0.
Mhm.
That's what's happening in real life. I have to represent real life as some type of theoretical information. Right, so if I say something's FF, what I'm really talking about is a sequence of 4 clock ticks that have all read a voltage that's above a threshold.
Okay.
Sorry, 8 ones.
Why
Yeah.
did we go from 5 to 8?
9 to 8, because here's why. This is the only reason why. I need a convenient way to represent more than 10 numbers in one spot, one place. Because I'm going to say that this X right here represents 4 bits. 4 bits. If I continue them all out and list all the possibilities, means that I can hold 16 items in that list of possibilities. I have to have a way to represent the final A, B, C, D, E, F, 6 things. I can't use numbers anymore. Does that make sense? Okay. In England, before we had computers and we just had ships to send information, they would load the ships with all kinds of goods. And their number system of commerce in England was based on the dozen, the 12, the count of 12. So when I had items, I had 1, 2, whoops, I'm getting messed up. 3, 4, 5, 6, 7, 8, 9, 10, E, What does E stand for?
E,
You can count in a dozen.
11,
11
I get it. Okay, yeah.
and 12. So when I loaded the ship, I could write down the number of items that I had, or the number of crates that I had, or the number of items, and based on dozens. If I could talk about a gross was T12. 12 12s.
So in order to keep the numbering system convenient.
Yeah,
Because obviously in a single, like, we were talking about this at breakfast this morning, because I sent an email out last night about 10 o'clock. I'm like, my head is exploding. Please, we need to talk. What I equated it to was each one of those places